Alrighty, well, thank you for the introduction. So yes, as Helen said, I'll be talking about basically high throughput metal isotope geochemistry, so a bit on the technical side as well, but then also the applications of this. So I'll do things a bit back to front as well. So just so I don't forget to do it at the end, I'll take a moment just to thank Helen for helping get this project off the ground, or some of the results, or some of the work that I'll be talking about, and then also to Dave and Dominic, who were just out in the field with us from GSQ, and then also Peter from JCU, who was out with us as well. So I usually do a bit of a preamble and just explain a little bit who I am, but I've actually met a number of people in here at least once or twice before, so I'll probably skip that a bit, and I'll just say that one of the things that I really like to try to do is build networks and work with people to try to get a multidimensional view of whatever's going on in a given area, and that'll sort of funnel into what I'm going to be talking about today. So I've sort of built this around the story arc of a book or a movie, or however you want to look at that. So this is basically just a bit of prefacing for the metal isotope stuff. So isotope geochemistry really centers around really only one type of instrument, which is a multi-collector inductively coupled plasma mass spectrometer. So there are a number of other ways actually that you can measure isotope ratios, but this tends to be one of the ones that will produce quite a bit quicker, and for most applications it's quite good at that. So that's abbreviated just as MCICP-MS for anyone who isn't really familiar with that. Basically, the whole idea is we just ionize the isotopes of an element, basically using an argon plasma that's burning about the same temperature as the surface of the sun. Kind of cool. We accelerate that down a flight path, and then basically, since those are charged cations, they will be deflected by a high-powered magnet. And if given the same charge, at least, that magnet's going to separate them based on their mass. So it's basically just inertia. And the way that that works is then a smaller mass is going to be deflected more. So then you have an array of cups, basically, which are just electronically conductive bits of metal. And once those ions hit it, they create a voltage. And we are collecting those all at the same time, hence multi-collector. And basically, that creates a voltage. And from that, we can tell what the sort of relative abundance of those isotopes for that element are. So this is a setup that we've got at JCU. So we do have one of these Neptune MCICP-MSs and also a clean lab to do all the sample prep, et cetera. So some of the stuff that we have been doing since I arrived there in February of this year is we've now got copper isotopes set up on our Neptune, and as well we've been setting up the chemistry for zinc isotopes. So we've been gearing up pretty quickly to be able to do this sort of work. And one reason that it's interesting to talk about, what's actually going on with the sample prep and all of that, is that it's not so easy peasy as it seems. So there's actually a fair bit that has to go into the samples before you can actually put them into the multi-collector. So basically you need to strip everything out except for the element that you care about. And that's because we have what are called spectral interferences. So a good example of this, so say we wanted to look at zinc isotopes. So we have the mass 64 zinc isotope. Turns out you also have a mass 64 nickel isotope. So if you put those into the instrument together, obviously that's going to muck up your results. So you need to actually get rid of that nickel. And as you can see on here, a whole number of other things. So stuff like titanium, barium, and then some other stuff, depending on what's going on and in what proportions they are, don't affect things so much. But in the ideal scenario, all you have in there is the one element that you care about, and that's going to give you your best accuracy and your highest precision. And I put a table down here just to show that there's actually a whole slew of these, and it's a really big problem with isotope geochemistry in that it slows everything down, because we have to basically go through the motions of getting rid of all of these interferences before we can reliably measure things. So the way that that's normally done and conventionally, and has been for at least the past 20 or so years, is just through ion exchange chromatography, and usually that's manual ion exchange chromatography. So the idea is it's basically working the same way that your normal sort of water filter would for your jug at home and your refrigerator, except instead of just catching those metals and then chucking it out when it's reached capacity, we are using a selective cartridge basically that is going to lock up the metal that we care about, then we'll flush everything out, and then we drop out the element that we're actually concerned with. And that's basically how it works. And so what I've shown on here, so this is just sort of schematically what it would look like. On the top here, so we've got our columns, we've got a resin in there that's going to, again, trap the element that we care about, wash everything else out, and then after the dashed line, that's when we're eluting the thing that we care about. And then we can sort of, usually we have to do a bit more prep, and then we can send it into the instrument and get our isotope ratio. And on the bottom here, this is just what's called an elution profile. So that's sort of telling you what's happening with the elements as you go through this process. So you have all of your matrix elements. The y-axis here is just telling you sort of the overall proportion of that element that we loaded onto the column. So we'll usually elute that out with one type of acid, and then when we want to actually strip off the element that we care about, we usually switch it to something else. So that's what's happening on the other side of that dashed white line. And there, that's for zinc. So then basically what you want in the best case scenario is this nice strong peak where you're pulling everything off in one go. You can actually cause fractionation on the columns of the isotope. So we also need to, in general anyways, make sure that we're getting about 100% yield. So you need to be extracting everything off of there. And then again, as I said, sometimes there's a bit more prep involved, but then we can put that into solution and run it through our instrument. So what's the big problem with all this? As I said, this conventional manual ion exchange chromatography, if you've ever looked at one of your jugs that has a little filter on top, it goes pretty darn slow actually. So you can imagine if you shrunk that down to 10 to 20 times smaller, it would go even slower. So say to do a dozen samples for zinc or copper or something like that, potentially end to end could take you something like a week, 2 weeks, depending on what's going on, how dirty the samples are, that sort of thing. So that's basically why I call it the Achilles heel of conventional isotope geochemistry. It's a real rate limiting step. So just as a bit of context, if you've got an ambitious isotope geochemistry project, so this is something that could take months or somebody really spends a whole year or something on the entire project, you may end up with 100 unique analyses. So if you actually want to turn this into a routine tool for something like ore exploration, and there's also medical applications for isotopes as well. There you're looking at something like 1,000 unique samples, or potentially even more. And you can see how very quickly that blows out into something that is no longer feasible by these conventional means. So boiling that all down, it's a scalability and translatability problem. And then into a bit of a buzz phrase, that's basically just workflow optimization that needs to occur there, and there are various ways we can do this. So now we'll move on to sort of a bit of plot development, why we actually want to do this sort of thing and go through all the trouble, one, of doing this sort of conventional method and or develop new ones. So why would we necessarily want to develop a new tool for ore vectoring for copper? So as I assume pretty much everyone in the room knows, copper goes into just about everything. It's in very high demand, and that demand is only projected to grow over time. Whereas, our techniques, there's going to be a crux basically in there, at which point it's going to get harder and harder to find the amount of copper that we actually need. If we're going to move to alternative sources of energy, as everybody again probably knows, that is going to require a whole slew of different elements. So this infographic over here on the right-hand side is just showing all the different elements that go into basically switching to alternative fuels and the different componentry of that. So that'd be things like electric motors, hardware, distribution of fuels, and then storage, so batteries basically. What you'll see is there's a whole variety of stuff in there, but what's in each one of those sectors is copper. So this is a really important one actually, that we need to figure out a better way to find this stuff and to do it more efficaciously and more efficiently. Okay, so how does it actually work then if you want to use copper isotopes as a vectoring tool? So the general idea here, and just in case I should circle back really quickly. So when we're looking at the isotope ratios, it's just the isotope, usually of a heavier isotope of an element over the lighter isotope, and then that is then put against the baseline. So a reference material that we use basically as our zero value. And then from there, everything is sort of held relative. So when we're looking at deposits and we're looking at solids, so this would be things like sulfides, usually your shallow late stage mineralization, if you're sort of moving upward, that's going to have a heavier isotope signature for something like copper. As you move deeper to the earlier mineralization and sometimes then presumably the higher grade stuff, then you may have a lighter copper isotope composition. Basically, that's just functioning because the lighter isotopes are going to react quicker, and so they're going to precipitate out first. If you have one reservoir of your copper, as you're basically extracting out the light stuff, what's remaining gets heavier and heavier. And so as you have later stages of mineralization, that's what you see. And that's how we can actually use it to vector in solids such as sulfides. When we're looking at waters, it's actually a bit the opposite, because you're going to find heavy copper isotope signatures when you're proximal to your deposit, and it's going to get lighter as you move away from that. And basically that's just working because you're going to, in general anyways, have oxidative weathering of those sulfides, which is going to take the copper 1+ that's in something like chalcopyrite, convert it to copper 2+ and put it into solution. When you do that, you're going to induce actually a massive isotope fractionation relative to a lot of other things that we see. And we can pick that up by, say, looking at bore waters that are overlying the deposit and then as you move outward. So summarizing all of that are the diagrams over on the right. So this is a bit cut off, so I'll just tell you what's going on there. So that's just the number of analyses for a copper gold molybdenum deposit in Alaska. So this is a Pebble Creek deposit. And basically in the water, so that's what the top histogram is over there. Basically when you're sitting right on top of it, you have a heavier copper isotope composition. And then when you move away from that, so you get more distal, then you have a lighter, then you have a lighter isotope composition. Down on the bottom, that's just the distribution map. So something that we're actually trying to resolve and figure out is what the halo of these things look like. So that's something that we're actively working on right now. And then again, the other bit over here, that's looking at core sulfide samples and basically summarizing diagrammatically what I was just saying before about the sulfides. All right, so this is actually useful on both sides of that coin. So when you have mining, you also, there's also an environmental factor that you have to take into consideration. So most of the time you're doing some sort of monitoring to look at environmental contamination. Turns out you could use the same exact tool to get a gauge on that as well, which I think is pretty convenient. So when you have things like acid mine drainage and you have these pH ranges that are actually can be quite acidic, then you will get heavy copper isotope signatures close to your tailings, and then that as you move away from it, so as you get to a less contaminated area, that basically drops to background levels. So this is just some more diagrams over on the right-hand side, just showing sort of one of the original papers that actually came out about how you could use copper isotopes to look at environmental contamination. And the one thing I'll point out here, so just the red arrow is basically showing that as you move distance downstream from the tailings, basically you get to a lighter copper isotope composition. And then the reaction there is basically just showing you what's going on with chalcopyrite and how you're actually releasing that copper 2+ into solution. So basically if you've got some water around and you've got some iron, then that's what you're going to do. And another great thing about this is that it doesn't actually matter how much copper is in the water. So what we're not looking at is just an anomalously high amount of copper. It actually matters not at all. As long as we've got enough water to get enough copper out of there that we can sample, it is working independent of the concentration. And so that's actually quite powerful as well, because as I'll point out a bit later on, element concentrations and element to element ratios are not always doing what you really hope that they're doing. Okay, so now that hopefully I've convinced you all that this is the tool of the future, I will talk about the more technical side of it and how we can actually push through this procedural barrier of ion exchange chromatography. So this is sort of summarizing what I was talking about before. So in the upper left, this is your sort of conventional extraction, so your ion exchange chromatography, and potentially you can actually strip off more than one element at a time, but that's actually a bit of a fickle process, and it's dependent on the type of sample that you have. So you sort of have to modulate or calibrate your chemistry based on what you're looking at. So you can see how that can get a bit clunky over time. And then the other means of doing this are basically pulling that solution through your column using a vacuum or pushing it through using pressure via some means. Usually that's a pump or a syringe-driven system. And then the sort of be-all, end-all of all that is you can combine one of those two, so vacuum or pressure, with an automated system that will then free your hands up, do the work for you so you can go and do other things. And those are sort of the things I'll be focusing on here. So one thing that I have developed and am bringing to JCU is what we've called spin chem. So it turns out instead of using like a big automated syringe-driven device or something like that, you can just chuck these things into a big centrifuge tube, stick it in a centrifuge, make sure you've got your speed right, and you get higher flow through your column. And that will actually do the same job with the same accuracy and the same precision, but about 5 to 10 times faster. So pretty convenient. Most labs actually already have a centrifuge, so it's actually pretty easy to build that into existing protocols. And another thing that's done but is not published yet is that I've done the same thing for copper using a different type of resin than what people conventionally used. And basically the whole idea behind that is the type of stuff that I'm using will strip out things like sodium much more efficiently, which, as you can imagine, for things like groundwater would be very helpful. And it turns out when you do this and you stick it in a centrifuge, sort of following the same concept, again, it will go 5 to 10 times faster. And that's, you know, a pretty big jump. So the great thing about this, and the corollary that I think you've all pretty much already drawn, is that we can use this probably directly on acidified waters. So the graph over here, or the two graphs anyways, over here on the left, one, this is published work that came out of someone's thesis, just showing, so the big blue bar there on the right-hand side, that's all your copper coming out very, very quickly. On the left-hand side, that's all the trash, basically the matrix elements that we don't want. And in there, you can see things like sodium, calcium, magnesium, so the major stuff that you'd want to get out of there. And that all comes out very, very efficiently. So again, I've done this in the centrifuge and made it go even faster. And the greatest thing about this is it doesn't actually depend so much on the type of acid you're using. Basically, as long as you pipette enough acid in and get the pH right, you can just chuck it on the column and you ought to be able to separate your copper very easily, which again is actually speeding things up by a day or two just because you don't have to digest your samples and take them back up in a different acid. So the other deal that we can do with this instead of the centrifuge is, again, we can use a vacuum to do this. So it's pretty well established with this copper purification protocol that I've been talking about that you can do it at higher flow rates. So you're just one way or another getting more fluid through your resin at a time. And we know that the isotope ratios that come out of this are really reliable. So this is just an automated instrument down here, just showing that you can actually do this in automated systems as well. So we know all that's true. So we can do this in a vacuum box as well. And the really great thing about this is if you have like little bits of other things in there that you need to make sure that you're stripping off. So say you have enormously high titanium or something like that in your samples and you need to get rid of it, you can just stack these things on. And that's something that you can't necessarily do with an automated system because most of the time they basically only got one spot for your chromatographic resin and you can't really just go in and chuck another one on the end there. So that's the idea there. And in general, this is using hydrochloric acid. And then you can stack things again on if you want to get rid of something. Something else that I would actually like to try with this, it turns out, so I just did some sort of background work with this resin. You can do everything in nitric acid as well, which is the same stuff that everybody's acidifying their water samples with when they get back to their lab. So if you just get that to the right pH, potentially you can do this nitric acid-based protocol, put it straight through your column. When it comes back out, you can actually strip your copper off in the same acid that you need to put your copper into the instrument in. So potentially you're cutting out at both ends all of the sort of prep work that is involved. So you don't have to digest your samples potentially. You put it through your resin, you get your copper out, and then instead of having to dry that back down, put it up in another solution that then goes into your MC-ICP-MS, you just lop off all of that, you put it into the resin, get it out the other end, send it to the instrument. That's the idea. It's a work in progress, so we haven't actually gotten to that stage yet, but all of the background work points to it being a good idea. So the icing on the cake for all of this is that for groundwater samples, again, you can just acidify those and away you go. And a really great thing is if you wanted to do the environmental aspect and you were looking at acid mine drainage, the pH actually is about what you need anyways. So this is just looking at sulfuric acid and the pH that you would want. So this orange bar over here is just showing as that goes up, more copper is being stuck on the resin more efficiently. So basically, you could potentially take your acid mine drainage, just put it straight on your column, and then elute it out and send it to the instrument. And then one of the last things that you can do here is automation, as I said. So turns out that there's a couple different options that you can do here, but the great thing about this is it will take off, say, 6 or 7 different elements, one after the other in about 12 to 15 minutes, and it's doing it without you having to have your hands involved. And so that's actually incredibly powerful if we can get these things calibrated to strip out these elements to then do isotope analyses. And you can see over here, all of these are actually valuable to look at their isotope systems, except for cobalt, only one isotope. If we say wanted to just look at copper and zinc, the separation between these two is massive. So we could separate these out really effectively and then look at them. And potentially we can just hook this all up straight to the instrument, so we don't necessarily have to do anything besides get the initial setup and get everything tuned. So I'm just ending the presentation with just talking about what I've been doing, or what we've been doing for the better part of this week. So we've been doing some work in Mount Isa, looking at sulfides, so chalcopyrites and sphalerite, and then also groundwater. Without really saying too much, the results of that have looked very, very promising. And so we want to extend this out and start looking in other areas and see if we can pick up the same thing and in areas that are less developed. So we've now moved this out to the Jericho and Eloise copper gold deposits. So those two are very likely genetically related. So we've, for this project, sort of looked at them as one and the same. And the goal was basically just to target bore waters using boreholes, of course, and to get somewhere between 30 to 50 samples in about a 20 to 30K grid around those two deposits. And this is just an EM map basically showing where those are. So they're about 60K southeast of Cloncurry, I believe, something like that. And then this is what we actually did. So that was the same EM grid that's sort of overlain with our bore water map. So as you can see, and the scales down there at the bottom, so we did actually manage to get about a 20K wide by 30K tall grid with a pretty good distribution around all of those, around those two deposits. So we ended up with somewhere around 40 borehole water samples. And we also took some unfiltered ones because we're trying to sort of build this into that CSIRO guide that Joe was telling you about. So you could essentially retrofit this entire technique onto that existing protocol that they're already following. And then we also have taken, of course, some grab and core samples from Eloise, and we'll be getting the same from Jericho so that we can characterize the deposits themselves. And then while we were out there, we thought, why not? So we took some termite mound samples and some spinifex samples because those actually sample pretty deep and tap into the groundwater as well. So we're just going to have a look at those as well and see if we can actually correlate those with the groundwater samples. And this is just a list of all the things that we are measuring. Joe very kindly basically went through all of that already. So the only thing that we're adding on to that basically then is the copper isotope. So what that's going to do actually is give us the most complete picture that I think anyone has gotten, or at least by common knowledge, that anyone has gotten for hydrogeochem with a deposit anywhere. And the last thing, which hopefully will whet the appetite of somebody, is we want to extend this to other places as well. So something, or a place that everybody's quite interested in, is the Cobar Basin. This is a borehole water map of that area. What you can see is it's pretty darn sparse in the Cobar Basin for water. So another thing that we may want to look at, so I hinted at it talking about the termite mounds and the spinifex, potentially in areas like this, we wouldn't want to sample water. We would want to sample something else that is tapping into whatever water is there. And so this was actually, these are screenshots from a presentation last month from Joe Schifano, who was looking at cypress pine needles. So idea is the same. You're tapping into the groundwater. Eventually that's coming up into the plants, and you'll be able to sample that just in the needles. So they did basically the entire Cobar Basin, something like 3,000 samples. So a pretty massive project, but actually pretty efficient because you just go by the roadside and pick some needles off and put them in a bag. You can actually micro XRF those just on the roadside while you're going about your business. And what they did see was when you have deposits, you will often find anomalies for certain metals, some better than others. So this is zinc, manganese down on the bottom. Actually, the best ones were things like tungsten, lead, arsenic, and a few others. And that's basically what this two-factor map is showing you. So things like lead, antimony, tungsten, arsenic are pretty good indicators of mineralization if you're looking in cypress pines. Interestingly, copper is not on there. The reason it's not on there and the reason zinc's not on there is because they're nutrients. So they're nutrients for the plants themselves, which means they're gated. They're only going to take up as much as they need so that they don't go toxic and kill themselves, basically. The really cool thing we could do with this is actually take existing samples from these pine needles because they've got something like 95 grams left that they haven't touched of these, and then just look at the copper isotopes. And hopefully anyways, that would prove the point I said earlier about it not mattering about the concentrations. You could just look at the isotope compositions because it should be sampling the copper isotope composition of the water that the plants are taking up. And that is it. So I'll leave it open. I think I probably went over.
No, you started late. It's all good. Any questions for Brandon? You bamboozled them. Well, I think you need to come back and tell us all about the results from Jericho and Eloise in another
Will do.
few months. 'Cause,
I have a comment.
oh,
You guys have been working really well with that, and I just wanted to, we're sponsoring the project, and this is a really good update. We're not able to really talk about it too much yet for the confidentiality reasons, but a real kudos to you guys at JCU. You've really, really done some really good science here, and I can't say how pleased I am to see you extend it to biogeochemistry with spinifex and cypress pine as well. Our spinifex, we've noticed the same bio issue with zinc and copper as well, and lead has turned out to be something very interesting to us as well. So as a potential.
Yeah. Oh, awesome. Thank you too, Trevor.
Hope I spoke that loud enough, but yeah.
Yeah, thanks for that. I don't think this is on. That's okay, I can speak loudly. Doesn't show up.
it's just for the, yeah, for the online people. Hold on. Try again.
Hello, does that work?
Give it 2 seconds.
Okay.
Yep, try now.
Yeah, okay, so there we go. So my question is, you mentioned that there's a slight fractionation during the formation of a copper deposit, and then the obvious oxidation overprint. I'm clear about the oxidation effects and what that does. But my question is there really a discernible, measurable fractionation of copper during copper deposit formation? And if there is, how do you separate that from the oxidation effect later?
Yeah, it's a good question. And I think my answer would be that, as I mentioned, the isotope fractionation that we see, say, in the groundwater is so huge relative to what we're used to seeing in a lot of other contexts, that the fractionation that you would see within the mineralization stages themselves, it may not matter so much which stage you're actually hitting, because, so as an example, like copper isotopes in silicates or something like that, or meteorites, whatever, you may see a fractionation that's something like anything above like 0.1 per mil, so parts per thousand, is considered pretty significant, and people will argue over values like that. In these systems, we're seeing something like 2 per mil, so it's orders of magnitude larger actually. So long as we're over those sulfides, if there's 2 or 3 per mil of fractionation between the sulfides themselves, it doesn't matter so much, because what we're going to pick up relative to the sort of baseline value for groundwater that is not weathering sulfides is quite large. So whether we could use it down the road as a tool to sort of refine things is actually something that I'm quite interested in. But for the moment, we're sort of just picking up these signals and seeing, you know, how big the halo is and basically how effective it may actually be as a tool. And all of that is looking really promising so far. And then down the road, I think we could get a bit more, we could slice things a bit finer.
But you think there's high temperature fractionation?
Yeah. So you think that there actually is measurable fractionation at high temperatures?
Yeah, I mean, what we've seen, so I actually come more from cosmochemistry and stuff like that than I do from like orogenesis and those sorts of things. And even with heavy metals, where you would expect to see minimal fractionation, we do actually, contrary to, I think, popular belief at least 20 or 30 years ago, we see appreciable fractionations in a lot of systems where people just thought it wasn't going to happen. And namely, again, at high temperature, because you would think you get less fractionation at higher temperature, but we still actually see it just because the quantum mechanics are strong enough that you're still creating a sizable difference in the bonding environments for the isotopes. And so we do still see things.
Thanks, Brandon.